1 plus 4 divided by 2, that is 5 divided by 2. 5 divided by 2 is 2.5. That will get through 2 also. 4 is an integer, the largest integer that is less than the value. Okay? So this is how this algorithm works. Okay, the next few slides are quite straightforward. Here is to tell you that we cannot just base the next number of slides just to illustrate that we cannot just based on observation. We have to sometimes we have if the result is important, if the conclusion is important, we have to prove it. Okay. So based on one experiment here, draw point on a circle. So initially, if we just put 1 point, there's only one region. The whole circle. In the circle, there's only one region. If we put 2 points, we draw 9. Yeah. You will divide the circle into 2 regions, right? If you put 2 points. How about if you put 3 points? If you have 3 points, you will divide the circle into how many regions? 4 regions. 1, 2, 3, 4. Okay? So if you have 5, you will divide the circle into 8. If you have 4 points, you will divide the circle into 8 regions. 1, 2, 3, 4, 5. So if you have 5, you will divide the circle into how many regions? 16. Into 16 regions. So until now, as though the number of regions we can use a formula to calculate, right? As though we can use the formula. As though we can use this formula to calculate the number of regions, right? Follow just now the 2. That means following this formula, number of regions equal to 2n minus 1, as though this formula is valid until n equal to 5, right? So here, number of regions equal to 2n minus 1. 2n minus 1, that means 2, 1 minus 1, 2, 0. 2, 0 is 1, right? So it's correct. If it's 2 point, 2n minus 1, how much? 2n minus 1, that means 2 to the power 2 minus 1, that is 2 to the power 1. 2, right? Here, 2 to the power n minus 1, that means 2 to the power 3 minus 1, right? That's 2 squared, that's 4. So as though it's correct. But when we check the result of 6 points, you'll find that it is not correct. Because when you have 6 points, if you draw the 9, you'll find that you have 30 regions, not 32. Not 32, it's 30 regions. So this formula actually is not correct in general. Up to 5 points is correct, but once you go further, it's not correct. So you cannot just based on observation. If the conclusion is important, you need to construct a proof. So the remaining part of this unit we talk about using induction. Induction not only can be used to design to solve a problem. In other words, induction can be used to solve any problem, including constructing a mathematical proof. So the remaining part we talk about using induction to construct mathematical proof. So here the name of this method is called mathematical induction. That means we are still using induction problem solving techniques, but in this case we use induction to solve to construct mathematical proof. It is quite commonly used in computer science. So this method is very useful to prove that a property Pn holds for infinite number of natural number n greater or equal to 0. If you have a formula or you have a statement and it is to prove that the formula holds for any n, just now, the number of region, yeah. If you want to conclude that the number of region is always equal to 2n minus 1, then you will need a proof. You will need a proof. One way is to use mathematical induction. Certainly, just now the formula is not correct, right? Certainly, you cannot use mathematical induction to prove. If you use mathematical induction, you will find that you have some problem. So before we talk about mathematical induction, you need some understanding of the basic mathematical notation. Summation is something that you need to understand. Okay. How many of you understand this kind of notation? Summation is summation I from 1 to n. These are the index. I is the index. I is the index. I means the index for this summation, and inside the summation, there is something here, right? Expression. Usually it's expression. In this case, simple. It's just I. So that means every term here is I. Summation means add up a number of terms together, and since here is I, that means every term is I, and this I is the index. So the first term, the index is 1. The second term, the index is 2, etc. And here, show you that here we have n term. The index is to start from 1 to n. This is the limit of the last index. This is the value of last index. So this shows that for this summation, the index is to start from 1 to n, and the term of the summation is 1. Okay. So that means for when I equal to 1, the first term is I, right? I equal to 1, so that means I, 1, because I is equal to 1 for first term. Second term, I is 2, right? I is 2, so you just substitute I equal to 2 into here. You get 2, right? So all this add up to 2, 3. Last term is the highest index that is written here, n. So for last term I, you have to substitute with n. You get n. So this notation means 1 plus 2 plus 3 plus until n. Okay? So you need to read, you need to understand how to read this kind of notation in order to understand, in order to interpret a formula, because using mathematical induction, usually usually your formula may involve this kind of notation. That's why we talk about this notation now. Okay, so more specifically, if you have this summation 1 to 4, and since this is a term, right, just as I mentioned, so for I equal to 1, you get the first term. For I equal to 2, you get the first term. Yes, until 4. So that means you have term from 1 to 4. So first term, you substitute I equal to 1 into this expression, you get 1. Second term, you substitute I equal to 1 equal to here, you get second. Third, you substitute I equal to 3, etc. Then substitute I equal to 4, you get the last term. There is the last term because I equal to 4 is the maximum. The second formula, the second summation here, you see I squared, right? Inside the summation here is I squared, right? That means this expression I squared, this means the first term I is 1 here. The second term I is 1 again, but the term here is I squared. So that means the first term, you substitute I equal to 1 into here, you get the first term. That's 1 squared, right? You substitute I equal to 1, I equal to 2, you get the second term. I equal to 2 is the second term. And the last term is n. Get this? A more specific example is here. 1 to 3, I squared. So for 1 to 3, first term is substitute I equal to 1 into here, you get 1 squared. Second, I equal to 2, right? You get 2 squared. Third, I equal to 3. 3 is the limit. So you get 3 squared, etc. You may have this kind of summation also. Summation A, you need to understand this part in order to read the formula. Before you use mathematical induction, you must be able to interpret the formula, right? The formula usually involves this kind of notation. So summation I equal to 1 to n A. So just now I mentioned that this is a term in summation, right? This is a term, and this is the index for the first term, and this is index for the last term. But in this case, the term does not depend on I, right? There's no I there, right? A. What does this mean? That means the term is constant. Since there's no I here, I is the only thing changed. That means the first term is A, the second term is A, the third term is A, until every term is A. So since until n, there's the n terms. For this case, basic example is from 1 to n, so there are 5a add up together. This summation means 5a add up together. Okay? And likewise for this case and this case. So here, it does not mean that I have to start from 1. I can start from something different from 1. So I start from P, some 3, 4. I can start from 3, 4, etc. Okay? So A, I start from P to Q, A. So the term A here, if the term does not involve I does not involve I, that means the term is constant. Okay? So you add up P, when index equal to P is A, when index equal to P plus 1 also A, when index equal to Q is also A, all the way A. So from P to Q, how many terms? So the number of terms is P minus Q, Q minus P plus 1. If we start from index start from 1 to 2, how many terms? Index start from 1 to 2, how many terms? 2 terms, right? 1, 2 terms. So if you I go 1 to 2 term, right? 2 term means number of term is, when you want to calculate the number of term from index is 2 minus 1 plus 1, right? You have to plus 1. You can see from here, all the way there are 2 terms here. So if you want to calculate from the number of term from the index, it's always the last index minus the first index plus 1.
Sorry, go back.
Yeah.
The last two, the examples. No, the examples. 7, 8.
7, 8.
Correct. Like.
Oh, you mean you are saying that this one changes to 7?
No. I don't understand the part where for n, okay.
The
5 is here 5 numbers, right?
Yeah.
5 times. So how is this different? This one where it's 6 and here it's only 4. What I understand is like from the formula 6 minus 3 plus 1 is 4.
No. Here tell the number of term. Here I go to 1.
Yeah.
Here the first term, this is summation is the start from first term to fifth term. Start from index 1 to index 5. This summation. So for index 1, the term is this one, is A. But I is not there. For index 2, it's also A. Index 3 is also A. Index 4 is also A. Index 5 is the limit, that's also A. So together for 5A. And for this case, it's here, so this summation is to start index from 3. For index 3 is, this term is A. For index 4 is also A. For index 5, index start from 3 to 6. 3, 4, 5, 6.
You need to work downwards
Index.
to prove that can work upwards.
Oh, okay. Oh. No, I think it's the factorial.
Here, index start from 3 to 6.
No.
Yes, index start from 1
I
to 5.
don't really get this part.
So you can define summation
But I know the question is-
by starting index from one point to another point. The index is always increased by one, from a preceding term to the succeeding term.
And then Q not necessarily has to be a number. The Q over there.
Oh, you mean those
the
are-
next number.
No, I mean like, let me see.
It can be
You
any
should
number,
take
it can be
this
any
from
number,
what is
right?
there.
This is a notation, general notation,
Yeah.
variable. We make it as a variable. Here is this value must be higher or equal to this value.
If I'm not wrong,
This is a variable.
if
Here
I'm not wrong, this
we
is
have a basic case.
no, this
That's
is
why
because-
constant with basic
The
case.
other one is what?
Yeah, with something like
You must prove, eh.
Yeah.
something like you can n square.
Doesn't matter the.
You can general you can
Okay,
use
yeah.
n square to denote the general value. But with n equal to 1, here it's
Eh,
1
he
square.
extend already.
Now is that already? Until when?
25th.
Which is?
Yeah, get back to you on that later.
Yeah.
Serious ah?
Yeah, just so.
Then I take
So here have a basic term. Okay, then property. Okay, property and Pn, property can be a formula, a property can be a formula, can be a statement. Okay, after introducing the notation, then let's say Pn is this property, Pn is this property. So in general, in using mathematical induction, it's very commonly used to prove that a property Pn hold for any n. So in this case, our example here, this is a property.
Just solve the thing.
Okay, what does this property mean? This property means when n equal to 1, when n equal to 1, that is P1, the property is P1, that means when n equal to 1, we substitute n equal to 1 into here, and we substitute 1 into here. That means when P equal to 1, this is the formula. Okay, this is the formula. Summation I equal to 1 to 1i, then n substituted with 1.
I never check.
This is a formula.
I assume
This is a
it's-
formula.
yeah,
When
yeah.
n equal to 1. And this is a formula when n equal to 2. When n equal to 2, that means we have to
No,
summation I equal to 1 to 2. 1 to 2. And the right hand side will be substituted with n equal to 2 also. You get this. So when n equal to 3, again you just substitute n equal to 3 into this formula, you get the property for, you get P3. That's the formula when n equal to 3. So when we have such formula, the different n value, you get a different specific formula. So there are many formula, in other words. Since n equal to 1, there are infinite number of specific formula. Every value for n, there's a specific formula. So this is the specific formula for n equal to 1. This is a specific formula for n equal to 2, etc. So mathematical induction is commonly used to prove such formula. Okay, and here I have another case. The formula can be represented in this way also. So what does this formula mean? Okay, when n equal to 1, we denote the formula by P1, and when n equal to 1, the right hand side is very clear. You just substitute n equal to 1, right? How about the left hand side? Left hand side means here, if the formula is represented in this way, it means the term. When n equal to 1, there's only one term. The term is, the value of the term is calculated by this expression. You substitute n equal to 1 into here. Okay, so 2n minus 1, 2 times n minus 1. Okay, so this is the formula when n equal to 1. You substitute n equal to 1 into here. N equal to 1, only got one term. Okay, when n equal to 2, you got two terms. Okay. So that means you use this expression again for calculating the first term. When you substitute n equal to 1, you will get the term for the first term, value for the first term, expression, specific expression for the first term. When you substitute n equal to 2, you will get the specific expression for the second term. Okay? So n equal to 2, there are only two terms. Then right hand side is a value. Okay? So when n equal to 3, this is the formula. This is the formula to n equal to 3, there are three terms. The first term, you substitute n equal to 1 into here, you get the first term. The n equal to 2 into here, you get the second term. You substitute n equal to 3 into here, you get the third term. Okay, so here n equal 3. So the last term is n equal 3. Okay, so right hand side you just substitute n equal 3 into here. So this is the formula when n equal 3. Okay, so this we are going to prove this kind of formula using. Okay, now mathematical induction. So mathematical induction is using the induction problem solving techniques to prove mathematical statement. So Pn, okay, we can use Pn to denote any formula. So to prove that Pn hold, to prove that formula hold, in other words, using mathematical induction, there are two steps. The first step is the basic step. Prove that Pn 0, the smallest n hold. The basic step we have put for solving problem just now. We solve the problem a smaller size, right? In mathematical induction, we prove the formula for the smallest n under the basic step. So under inductive step, we will have an induction hypothesis. So assume that this induction hypothesis, Pk hold for k greater than or equal to n0, assuming that the formula hold for a particular k, and this k certainly have to be larger than the integer that the formula hold, larger or equal to the integer the formula hold. And that means under the inductive step, assumption is always assume that formula hold for when n equal to k, and we use it to prove that the formula also hold for n equal to k plus 1. So if you can do this, then from the principle of mathematical induction, Pn hold for any n greater than or equal to 0. Okay, now we prove a simple formula here, go through the steps. Okay. So there are two steps here using mathematical induction. Now we want to use mathematical induction to prove this formula. So just now those notation I introduced is for you to, in case you do not have too much mathematical, in case you don't have too much exposure to mathematics. So it's for you to interpret this kind of formula. In order to prove, you have to understand this formula. What does this formula mean? Okay. So under the basic step, you have to prove that the formula is true, is holds for n equal to 0 when n equal to smaller value. Smaller value in this case is stated here, right? The smaller value n greater than or equal to 1. So under the basic step, you have to prove that the formula holds when n equal to 1. Okay. So we prove it for n equal to 1. Okay. How to prove it? We check the value of the left hand side and the value of the right hand side. If we find that the value of the left hand side and left hand side equal, that means the formula hold, the formula is true, right? When n equal to 1. So what is the value of the left hand side? The left hand side value in this case, for n equal to 1, we just substitute 1 into here. 2 times 1 minus 1 is 1, right? It's 1. Left hand side is 1. Right hand side, we just substitute n equal to 1 into here. That's 1 squared. So both are 1, right? So that means when n equal to 1, the left hand side equal to right hand side. That means the formula hold when n equal to 1. Okay, so we have completed the basic step. Okay. So there are two steps. After the basic step, we have to proceed to the inductive step. Okay, under the inductive step, this is a formula, right? 1 plus 2 plus 1 plus 3 plus 5 plus 2n minus 1 equal to n squared. This is the formula. So under the inductive step, we always assume that the formula is true when n equal to k, n equal to k. Okay? And we use it to prove that the formula is true when n equal to k plus 1. Okay? So we assume that the formula holds for n equal to k. Okay? Since we assume that the formula is true when n equal to k, that means we have this. We have this, right? That means when we substitute n equal to k into this formula, the formula holds. That means that's our assumption. So 2k plus minus 1, when we substitute n equal to k into here, we have 2 times k minus 1 here, then equal to k squared. We have this. We have this, right? This assumption. Then we are going to use it to prove that formula is true when n equal to k. But before we can prove it, we have to see that what is the formula? What is the formula when n equal to k? Okay, we check the left hand side of the formula when n equal to k plus 1. That means we substitute k plus 1 into the formula. Substitute k plus 1 into the formula. When you come to here, That means every term is expressed in terms of 2n minus. So k plus 1, the k term is 2k minus 1, right? So the k plus 1 term, k plus since is 2n minus 1, that means we plus the k term will be 2k minus 1, then plus 2k, k plus 1 term, 2k plus 1 term means n substituted with k plus 1 minus 1. Okay, we have this plus 1 plus 3 plus 5, etc. That means when n equal to k plus 1, this is the form, this is the left hand side. Okay, I'll show you just now. This is the left hand side. Then what is the right hand side? Right hand side is very straightforward. Right hand side is n squared, right? When for k plus 1, that means n substituted with k plus 1. So we get this. So this is the left hand side, and we can okay, this is the left hand side, and left hand side we can simplify, right? Because we already have this assumption. Until k term, this is the sum. Until k term here. So for k plus 1, actually the first k term exactly the same with this this one. Exactly the same with this one. So we substitute. That means we can substitute k squared. We can replace the whole thing by k squared. Because we have already assumed that the formula true, where for n equal to k, that means we have this. So we replace this part. It's exactly the same with this. So we can substitute this, replace this with k squared. Once we replace this with k squared, we do some factorization. This is k from simple algebra, k squared plus 2k plus 1 is k plus 1 squared. Right? Okay, this one you can refer to basic algebra book. 2k squared plus 2k plus 1. Because I think no time to go through all this after. You can ask me. I think the basic mathematics, all the O level, the A maths we have. Either O level A maths or the so-called A level maths we have. So right hand side, you substitute n equal to k plus 1, right? Just substitute in. So you can see the right hand side. After we substitute n equal to k plus 1, exactly the same with right hand side. So the same, right hand side both the same.
Is it always n equals to k plus 1 for all inductions problem?
Oh yeah, that's in induction. In fact, if you have some mathematics background, induction is easier than using general induction to solve problem. Using mathematical induction, in fact, is easier than using induction to solve problem. Both are using induction actually, but because in mathematical induction, there's always a standard framework for you to follow. But induction to solve general problem, sometimes you need to based on your design, and there's no general structure to follow. In this case, they always that is relating to the question asked. Okay, we always assume that k is true and use it to prove k plus 1. Yes, okay. And this is the way. Okay, so after you complete the inductive step, that means the formula hold. Yeah. We can use from the principle of mathematical induction. That means we can conclude that the formula hold. The formula definitely hold. If the formula is not true, you won't be able to complete all the steps unless there are any mistake. So we concluded. Second example. So this is slightly more complicated example. We prove using mathematical induction, prove this formula. Then basis step for n equal to 1. Again the same thing. We check the left hand side. Left hand side n equal to 1, there's only one term, and the term is n squared. So the term is 1 squared, and Okay, so after you calculate, the value is 1. For right hand side, you substitute n equal to 1 into right hand side and you find out the value. Okay, so it's quite 1, substitute n equal to 1 into here, you get this, and you get 1. And you get 1. Okay, and the value for the left hand side and right hand side is equal. It's equal. Okay, we have a few more slides. We finish it first. Then after that, we come back for the greedy approach. So the formula hold. Okay, so basic step completed. So we proceed to inductive step. You see, from here, again, we assume that the formula is whole for n equal to k. Okay, when the formula is whole for n equal to k, that means when we the formula for n equal to k is true. We have the formula for n equal to k, in other words. Okay, so the formula for n equal to k means you substitute left hand side with k and substitute right hand side with k, and that is equal. That is equal. It means we have this. We have this. There's the assumption from induction hypothesis. We have this formula. You can make use of it. You have this, that means you can make use of it. Okay? Then we make use of this to construct the proof for n equal to k plus 1. So when you want to construct a proof for n equal to k plus 1, you must always use this formula. Definitely you have to use this formula. If you do not use this formula, that means definitely you won't be able to construct the proof. Then, okay, now we proceed to prove the formula is true in n equal to k plus 1. Okay. So for n equal to k plus 1, if you substitute to the left hand side, you will get this. You will get this. Then you observe that actually until k term is exactly what we have here. Exactly until k term. So we can replace the first k term with this expression. Okay. With this expression. Okay. Then so now the value gets simpler, neater. Then we do some factorization. Both k plus 1. Yeah, both k plus 1. We can do some. We can bring out later. We can bring out factorize out. Factor out k plus 1 because here I have k plus 1. Here also k plus 1. We can factor it out. Involve some basic algebra. So here we take it out. So inside is this. Then we further factorization. This one, 2k plus 1. Factorization. Okay, this one you can refer to O max, O level max, A max, definitely. O level, I think some E max may have also. O max definitely, A max definitely. Okay, this example doing factorization, but if you are not comfortable with factorization, actually there's another method. Okay, after you factorization, right hand side you check the right hand side, left hand side the same. So you prove the left hand side and right hand side. So from principle of mathematical induction, we conclude the formula hold. So next example. This not another example. This is the another proof for example 2. Another proof for example 2. Okay, just now we do quite a number of factorization, right? So in case you are not familiar with factorization, so the first step is the same. Basic step to prove the left hand side equal to right hand side. Calculate the value because basic step always calculate exact value. So usually no factorization involved. Just calculate value directly. As far as you know how to interpret the formula, there is no problem to do basic step in the end because you calculate exact value. Okay. So when you come to the inductive step, usually involves some factorization or expansion. So the earlier proof we use factorization. Now in this proof, I'm going to do it without factorization in case you are not familiar with factorization. Just expand it. So assume the formula is true when n equal to k, that's this one. Okay, the same thing. So right hand for n equal to k plus 1, left hand side is the first k term is exactly what we have under the induction hypothesis. Okay, so we substitute in here, we replace by the right hand side from the induction hypothesis. Then we get this. Then we get this here, over here. We get this. This one is from the induction hypothesis. That means the sum for until k term. Then plus this one. Then since if we don't want to factorize it, then we just make them have common denominator. Then after that expand all the way, expand everything out. Expand it. Just time it out. Time everything out. Then you get this for the left hand side. Everything time out, expand it until individual term. For the right hand side, again you expand it all the way. Expand it all the way, then you'll find it. The expression from the left hand side and right hand side equal. Okay, compare them, they are equal. So that means you have proved that left hand side equal to right hand side for n equal to k plus 1. It means you have completed you have completed the proof. Now from principle of mathematical induction, you have concluded of the formula proof. Okay, any question?
How do you know when to stop?
Again?
How do you know when to stop expanding or stop factorizing?
Oh, yes. Okay, you see here, all individual term already. There's no way to expand. Individual term.
So you reach
You
to
see here,
maximum.
you see here, haven't finished yet. Yeah, 2 factor, right? This time this one, right?
Yeah.
So we know we still have to continue. And here we know that we have reached the bottom or expanded already. Individual term, right? So this is the point to stop or expansion. Right? Right. Same thing for the earlier one. Expand, here still can expand. Here still can sum up. The common term have to sum them up together. Oh, right? But here you reach everything, all these terms are different. K cube cannot add together k squared. Right? So this is a stop for expansion. How about, okay, now go back to your another question. Factorization. When do you know? Yeah, everything is a factor. There's no other thing involved. Factor.